Hello, everyone. Have you ever wondered why some molecules are strong and stable while others break apart easily? Well, a big part of this difference comes down to bond parameters. Bond parameters are like the fingerprints of a chemical bond. They tell us about its strength, length, and shape. Think of it as a recipe where each ingredient plays a critical role in the final outcome. So, what exactly are these bond parameters? They include bond length, bond angle, bond enthalpy, bond order, and resonance. These concepts help us predict the behavior of molecules and understand everything from chemical reactions to the stability of compounds in everyday life. Today, we are diving deep into these fascinating aspects of chemistry. Let's start with bond length. Bond length is simply the distance between the nuclei of two bonded atoms in a molecule. You can think of it like the space between two people holding hands. The closer they are, the stronger the bond. The length depends on the size of the atoms and how many bonds they form. For instance, a single bond between two hydrogen atoms has a bond length of 74 picometers, 74 pm, while a triple bond between nitrogen atoms is much shorter. This is because triple bonds pull the atoms closer together. Bond lengths are crucial for understanding molecular geometry and the physical properties of substances. So, just like how the size of an object affects its fit in a space, bond length determines how atoms are packed together in a molecule. Now, let's talk about bond angle. Bond angle is the angle formed between the orbitals that contain bonding electron pairs around the central atom. Think of the bonds as spokes on a wheel and the bond angle as the angle between those spokes. For example, in a water molecule, the bond angle between the hydrogen atoms is 104.5 degrees, 104.5 degrees. This bond angle is essential for determining the shape of a molecule. Just like how the angle between the legs of a tripod determines its stability, the bond angle influences the molecule's overall stability and reactivity. For molecules with more complex geometries, these angles can tell us how the atoms are arranged in three-dimensional space. And believe it or not, understanding bond angles is key to explaining why water behaves the way it does and why molecules like methane are tetrahedral. Let's move on to bond enthalpy. Bond enthalpy is the amount of energy required to break 1 mole of bonds in a molecule, and it's a measure of bond strength. In simple terms, stronger bonds require more energy to break. For example, the bond enthalpy of a hydrogen-hydrogen bond is 435.8 kilojoules per mole, 435.8 kJ per mole. This means it takes 435.8 kilojoules of energy to break that bond in 1 mole of hydrogen molecules. The higher the bond enthalpy, the stronger the bond. So, for molecules like oxygen, O2, or nitrogen, N2, which have multiple bonds, their bond enthalpies are much higher, 496 kilojoules per mole, 496 kJ per mole for oxygen, and 946 kilojoules per mole, 946 kJ per mole for nitrogen.
Stronger bonds generally mean more stability, and that's why nitrogen is so unreactive under normal conditions. Its triple bond is incredibly strong.
Next, let's explore bond order and resonance structures. Bond order is the number of bonds between two atoms. In a simple molecule like hydrogen, H2, bond order is 1 because it has a single bond. But in oxygen, O2, bond order is 2 because it has a double bond. This bond order helps us understand how strong the bond is. Higher bond order generally means shorter and stronger bonds. Now, not all bonds fit neatly into one bond order. Take ozone, O3, for example. It doesn't just have single or double bonds. Instead, it's best described as a resonance hybrid, where the electrons are delocalized across the molecule, making both the oxygen-oxygen bonds intermediate between single and double bonds. This concept of resonance is crucial in understanding molecules like carbonate, CO3, where the bond order is fractional because of the delocalized electrons. So, while a single Lewis structure can't capture the true nature of these molecules, resonance gives us a more accurate picture of bonding. Finally, let's discuss bond polarity. A bond is polar when the electrons are not shared equally between the two atoms. This usually happens when there's a significant difference in electronegativity, the tendency of an atom to attract electrons. Take hydrogen fluoride, H-fluorine, for example. Fluorine is much more electronegative than hydrogen, so the shared electrons are pulled more towards fluorine, creating a polar bond. This difference in electron distribution gives rise to a dipole moment, which is a measure of the polarity of a molecule. The dipole moment depends on both the size of the charge and the distance between the positive and negative ends of the molecule. For molecules like water, H2O, the dipole moments of the individual bonds add up, giving the molecule an overall dipole. On the other hand, in molecules like carbon dioxide, CO2, the dipole moments cancel out because of the linear structure, making it nonpolar despite having polar bonds.